the acid, this part here, the 1 and H3O plus, obviously that's going to protonate the enolate to make the ketone. And then since you have excess acid here and water, this is eventually going to hydrolyze the saminium to the ketone. Okay, so what I'm getting at is in the end, you should have a 5-member ring with a carbonyl, and then you should have a carbon chain at the alpha position of the carbonyl that has 1, 2, 3, 4 carbons and a carbonyl here. Okay, really what I want you guys to focus on is step 2, using KOH. So how can you go from KOH to that intermediate? That product, I should say. Sorry, come back. All right, so let me go ahead and stop sharing. All right. Can you guys see the document camera?
Yes.
All right. So what I have here is this molecule here. So let me actually go back to the PowerPoint. I'm sorry. So what I want you guys to think about, as I pointed out to you guys, the first step here with acid is obviously going to protonate this enolate to make the ketone here, right? So this becomes a ketone. I'm just going to put a hydrogen there. In addition, the acid and water will basically hydrolyze that imine to the carbonyl. So I should have a diketone here, okay? But the thing I want you guys to recognize is I have a diketone, right? So I have two carbonyls that are both ketone. And then I want you guys to look at this product. And I want you to start speculating something about this product. What I tried to teach you guys yesterday, this is basically an aldyl product that has been lost water. Okay, so it's an aldyl condensation product. And again, what I want you guys to think about with this is that the carbonyl is retained here, but recognize that at this alpha position, this carbon here is my nucleophile always. So in order to make this new bond here, this is the new bond that I'm forming, the alpha and the beta bond. Every time whenever I do an aldyl condensation, the new bond being made is this alpha carbon and that beta carbon, where the alpha carbon is my nucleophile and the beta carbon is my electrophile. Kind of in line with what I talked about today, right? In microadditions, the beta carbon is always electrophilic. Why? Well, you can also think about how it's formed. This carbon here was originally a carbonyl.
Sorry, we can't see the PowerPoint
right now because we can just see your piece of paper.
I'm not sharing. I'm sorry. Sorry about that. Okay. Sorry about that. Let me share. You can see it now?
Yes.
Okay. So what I'm getting at is I want you guys to see this product here. So I apologize. Let me start back here. So the first step here is obviously going to protonate this enolate here. So I'm going to add a proton here. That's going to make a carbonyl. Okay, so that's going to make a ketone there. And as I pointed out to you guys in the preceding slide, amines hydrolyze under acid and water to also give you a carbonyl here. Okay, so all of you should draw a structure that has a ketone here and a ketone here. Okay. Now recognize that ketones can react with themselves to make an aldyl product. This is an aldyl product. This is what we just talked about in chapter 23. This is an alpha-beta saturated system. Now what I'm asking you guys to recognize is that the bond that's being formed whenever I'm doing an aldyl condensation reaction is the alpha and beta bond. So this is my new bond in that reaction, going from that diketone to this product. So also recognize, and this is what I mentioned yesterday, is that this carbon right here, the alpha carbon, is always going to be nucleophilic. Consequently, this carbon here is always going to be electrophilic. So this alpha position is my nucleophile. That's going to be generated from a enolate. Whereas this carbon is going to be my electrophile. That's going to come from a carbonyl. Okay, so if I want you to think about that, because I'm going to stop screen sharing and I'm going to go to the document camera and just showcase that this is just an aldyl reaction that I'm asking you to do. So all of you guys can see my screen, right? My document page, piece of paper?
Yes.
Okay.
Yeah.
So that's what I did here. I just showed that intermediate, and then that first step of acid gives you that ketone, and I just redrew that ketone to there. Okay? I'm not going to show the product, but all of you should recognize that in the first step here, that second step with KOH or hydroxide, this will involve basically taking this proton here and generating the enolate. Okay, and again, I should show this reversible because we're on weak base.
Why would you take that proton off?
Because I was trying to explain it. I knew that by looking at the product.
It's a big base too, so that's the one that is.
Well, just let me go. Let me go with this. I don't have the document in front of me. Here, I'll put it down here. I knew that by looking at the structure of the product that's asking. If I didn't give you this product, then I would have to start really thinking about this. But the fact that I'm giving you this product, I'm asking you to use it. Okay? Whenever you have an alpha beta unsaturated carbonyl, this is always my alpha position, which is nucleophilic. This is always my beta position, which is always electrophilic. Okay? So in other words, the bond that I'm going to be making is this bond here. And in an aldol reaction, this is going to mean, that I'm making an enolate here, and I'm reacting it, I apologize, I'm drawing this kind of ugly, and I'm treating that with a electrophile here. So at some point, this carbon is going to attack that carbon. I knew that just by looking at this connection here. Okay? So the reason I started with this proton is I knew that's the enolate I need, right? That's what I have here. So at this point, it's very easy. All I got to do is just showcase in the mechanism that this is just an aldol reaction. I'm going to attack that carbonyl carbon. The oxygen is going to go up to the tetrahedral intermediate. Try to draw a nice 6-member ring. Okay. Now, next step is that when I deprotonate this, I generate water. So I have water. This electron pair, it's going to attack water. You gave me the beta hydroxy ketone. Okay. And then the last step in this transformation, because I'm in base here, is the E1CB. So remember, anytime you're in base, think E1CB. E1CB says I still have an alpha proton there, so I'm going to make the enolate by taking hydroxide here. Abstracting a proton to make the enolate. Okay. So now that I have that intermediate, the next step is to do the elimination. So that negative charge comes here, and hydroxide is my leaving group. And finally, I form the final product. Oops. Okay. So again, the point that I want to make to you guys here is if I ever asked you to do a synthesis of an aldol, or if I gave you guys an alpha beta unsaturated aldehyde or ketone, I want you to look at that molecule and recognize right away you know how to break it. This double bond is always being formed, and the alpha position is always going to function as my nucleophile, which this case means the enolate has to be generated there. And the beta position means that I have an electrophile. In the case of an aldol, or a ketone, that's a carbonyl. Okay. All right, let's go on to the next slide.
Professor?
Yep.
If we weren't given the product, how would we know which hydrogen to grab?
Let me come back to that later on, okay?
Okay.
I want to introduce this, and then I'll come back to that, because again, I want to be going back and forth. I want to finish here with the Robinson annulation. I don't think I'll get to the Mannich